Imagine swinging a rope around in a circle with a can attached to the end. The can is in a constant state of acceleration since its velocity is constantly changing due to its circular path. Acceleration of the can is caused by a net force acting on the object. In the case of an object moving in a circular path, the net force is called centripetal force or center-seeking force and is always pulling an object toward the center of a circle. Without this force, an object will continue moving in a straight line motion. The centripetal force is the tension on the rope. The centripetal force is equal to mass times velocity squared divided by the radius. As these variables change, so will the centripetal force. An increase in mass or velocity, or a decrease in radius, will result in an increase in the centripetal force. A decrease in mass or velocity, or an increase in radius, will result in a decrease in the centripetal force. A change in velocity results in the largest change in centripetal force. If the rope is cut, the can will no longer maintain a circular path, and it will fly in a straight line tangent due to Newton's first law of inertia. The force of gravity pulls the moon towards the center of the Earth. This pull is the centripetal force keeping the moon in orbit around the Earth. If Earth's gravity ceased to exist, the moon would fly off into space in a straight line. Another example of centripetal force is the force that binds mud to a tire as it rotates. As the rotation speed of the tire increases, the centripetal force will not be great enough to hold the mud onto the tire, and the mud will fly off the tire in straight line tangents. As we saw with the can that was attached to the string, the centripetal force is the force that creates the tension on the string, the center-seeking force. There are two perspectives in this example, outside of the can and inside the can. As Newton's third law states, for every action, there is an equal and opposite reaction. From outside of the can, there should be an outward reaction force to the centripetal force. This center-fleeing force is known as the centrifugal force. The reactive centrifugal force is the reaction force to a centripetal force. The can, undergoing curved motion, constantly accelerates toward the axis of rotation. This centripetal acceleration is provided by a centripetal force, which is exerted on the can by some other object. This is the reactive centrifugal force. It is directed away from the center of rotation and is exerted by the rotating can on the object that originates the centripetal acceleration. If an object is placed inside the can, the object appears to have an outward force pushing it against the bottom of the can and away from the center of rotation. The apparent centrifugal force is most commonly introduced as an outward force apparent in a rotating frame or reference. It is apparent or fictitious in the sense that it is not part of an interaction, but actually the object's inertia. The object naturally wants to travel in a straight line, but the centripetal force doesn't allow this. This type of force is associated with describing motion in a non-inertial reference frame and referred to as a fictitious or inertial force. The reactionary and apparent centrifugal forces are not real forces. The reactionary centrifugal force is a result of the rotation, not a force. The apparent centrifugal force is really the object's inertia. A more accurate definition for centrifugal force would be the lack of centripetal force. The concept of centrifugal force is used to describe the physics of rotating devices such as a centrifuge, centrifugal pump, centrifugal governors, and more. Even though centrifugal force is not a real force, it's commonly used because it's easier to describe the fictional force than describing the lack of the real centripetal force. Pumps that have an inlet near the center of rotation and an impeller that forces water outward against a volute to channel the water to an output away from the center of rotation are known as centrifugal pumps because the water is center-fleeing. The centripetal force is not strong enough to keep the water traveling in a circle with the impeller, resulting in the water moving out towards the pump volute. The physics of a centrifugal pump are not based on the imaginary centrifugal force, but the lack of centripetal force.